mode and go to the screen and whiteboard. One of these days I should clean up my desktop. Oh, well, sorry, this is clear canvas. This was so. Can you all see the whiteboard and can you all see the? Can you all hear me?
Yes, sir.
Yeah. So let us pick up. Let us think of some simple problems in the last class that we were talking about, which was codon bias, right? Now, let us say I give you a very simple problem in codon bias. Let's start with simple problems. Let us say I have a protein which I want to produce or express, and it is a 100 amino acid long protein. And it is a 100 amino acid long protein. And I think that the CAI, the codon adaptability index, should be greater than let us say 0.7 or 0.8, whatever you want to write, 0.8, let us say 0.8. It should be greater than 0.8 for me to get good expression, otherwise I will get into trouble. In order to get good expression, I need a CAI value of greater than 0.8. Right. And let us say that I have discovered that there is an arginine, R, I'll call it just arginine, which is coded for by a codon where the FAI, F frequency of usage of that particular codon upon F max is, let us say put it as 0.2, some number. And there is an isoleucine which is also F by F max is 0.2. And there are leucines, and I'm just putting easy numbers so that we can do a simple math. Real values must be obviously different. And where the F by F max is also, let us say 0.2. I mean, that's not really very important. 0.2. And there are not one but multiple isoleucines. There are many leucines. All of which, for example, let us, for the ease of simplicity, let us say that they're all 0.2. Now, the question really is, for example, I don't want to correct for this arginine and isoleucine. Now, how many leucines can I afford to have this kind of codon biased triplet codon? I mean, I don't remember what isoleucine is coded for. I mean, don't expect me to remember that kind of molecular biology, but suppose it's coded for by some, I mean, let us say TAG or whatever. Obviously false. I mean, I cannot guess what it is. Remember, there are 64 combinations, and I'm sorry, 64 combinations because the first can be either A or T or C or G. And similarly, the second combination can be 4. So there are 4 possibilities and 4 possibilities in the second and the 4 possibilities. So there are a total of 64 possible codons, out of which, as I remember, that there are 3 stop codons, not 1. So there are 3 stop codons. So actually 61 codons code for 20 amino acids. So I don't remember what it is, but let us say it is TAG and it is TAT and it is TAA or whatever. So on and so forth. And this is the most commonly used, so which has a probability of functioning of 60%, and you are always getting TAA. This is some probability. Let us say this is 15% or not 15, 12%, and so 12 by 60, it's always 0.2, some such number. I mean, I don't really care. We are just putting the numbers here for solving a problem. Now, how many isoleucines can you afford? How many leucines can you afford to have 0.2 and still have a CAI of 0.8 is the question. Before, or so when do you need to take corrective action? When do you need to take corrective action? And what corrective action will you, when do you need to take corrective action? I mean, can you afford 1 isoleucine? Can you afford 2? Can you afford 3? Can you afford 4 leucines? Sorry, not isoleucine, leucines. Before you start taking corrective action because you think that codon bias will impact on your good expression possibility. When do you need to take, and what corrective action will you take? Obviously, the corrective action that you will take is an answer in biology. Either you will use two strategies, and that answer I have already given you. Either you will use a strain which is modified such that R, I, and L, the tRNAs for R, I, and L, the tRNAs corresponding to R, the tRNA corresponding to I, and the tRNA corresponding to L, but having an anticodon loop of TAA, for example, rather than TAG, is also introduced. This gene for this is also introduced into the chromosome of the cell. So if you introduce the gene coding for the tRNA, which has an anticodon loop matching with TAA, then immediately this frequency will go up, because now you will have more tRNAs of containing the anticodon loop for TAA, and so this will no longer be 12%. But in the chromosome, the original wild type E. coli, the codes are for TAG mostly. So more of TAG based tRNAs are produced rather than tRNAs coding for TAA. So obviously these tRNAs are in short supply, and that is why this is 0.2. Right? So that is the corrective action. So one corrective action would be to introduce tRNAs, genes which code for that particular anticodon which is present in your gene, because you want good expression. And the second, of course, corrective action is harder, but nowadays has become easier and simpler, which is to take the gene and give it to a shop and say, Bhai Sahab, wherever there is TAG, please replace it by TA. Sorry, the other way around. Wherever there is TAA, please replace it by TAG, so that there is no codon bias. So you can actually remove it at the genetic level. By second correction is at the genetic level. So the second correction is at the genetic level. You simply change the codon, the genetic code. And nowadays, whenever you order genes from abroad or from India, where there are shops which allow you to buy these genes, you almost always tell them, please remove codon bias. And they obviously use the best codons so that your F is always 1. So the point really is that the F of all other of the 100 amino acids is all 1. So you don't have to bother. So every other amino acid is 1, but there is one R which has a point R of 0.2, and I of 0.2, and there are many L's which are also of 0.2. Now the question is, how many L's can you afford before the codon bias becomes a problem? So any answers? I've been repeating the question so that you sit down and solve it. How many L's can you afford? Remember that the principle, guiding principle is this. So now, answers. If not answers, at least strategies of how to solve this problem. So the question is, how many L's before I need to take corrective action? हाँ भाई, ये छोटा प्रॉब्लम है, मैथ्स का क्लास 11th 12th का प्रॉब्लम है, तो आप बता सकते हैं. I'll wait for a couple of minutes, hoping that you're trying to solve it. And I hope that you're also not waiting for some of your colleagues to solve it. I hope you are trying to solve it yourself. हाँ भाई बताइए, कुछ तो बताइए. Or shall I leave it for you people to solve? And we can have various modifications to this theme. I mean, I'm just sort of saying that this is the kind of very simple problems that you can think of when you are working with codon bias. Any opinions? Solution? हाँ भाई. What do you do? What is the codon bias that you want? Maximum 0.8, right? So let us say there are n, or let us say call it XLs present in the protein. So what would happen? What would be the codon bias if there are XLs present in the protein? Hello. So what is the CAI? हाँ भाई बताइए. Somebody should say something. There are at least 20, 25 students in the class. How many students are there in the class? Well, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Not a very good number, but still. Less than half the class is present. The remaining half tend to sort of think that they don't need to attend classes. But yeah, at least out of 20 of you, one answer. What is the CAI? The geometric mean. Pi 1 to I is equal to 1 to 100. Okay, and then these frequencies, let me call them f by f max. Let me call them W. The W multiplication of W's, right? Wi's f by f max. Now, so all these, the remaining are all 1. So it is 1 into 1 into 1 into 1, all of them till whatever number. So that we don't really need to bother. Into 0.2 into 0.2 into x, also 0.2 raised to the power of x, right? With there are x of them, and then this whole thing raised to the power of 1 by 100 is equal to 0.8, right? That is it. So you can find out x, and x should be less than that. So what is the answer? So what do we have? Hello. 0.2. 2 plus x raised to the power of, or is equal to 0.8 raised to the power of 100. हाँ भाई बताओ क्या होता है? So what is x? 0.2 raised to the power of 2 plus x is equal to 0.8 raised to the power of 100, and that is your answer. Correct? You go ahead and solve it now. I mean, I don't think I should handhold at the level of class 12th algebra. Can we get out of this problem? All of you?
Yes, sir.
Do you follow? Can all of you follow this?
Yes,
sir. Simple enough, right? So you need to be able to address these problems in a reasonable way. So you have to remember that it's geometric mean, so you have to sort of solve it like that. And if your calculator does not give raised to the power of 100 because it creates trouble, then you take log and solve it. Okay, taking log is easy enough. So 2 plus L log 0.200 log 0.8, and then you can sort of solve it easy enough, right? So you can just take logs if the number of amino acids are so large that your calculator is not taking it. So you can always take log or ln, and then all these things come into the multiplication factor. So you can have 2 plus x ln 2.2 is equal to 100 ln 0.8, and so 2 plus x is equal to ln of this plus divided by that. So easy enough. Now I will not solve many problems like this. As I said, just one problem because we don't have time, and you can think of similar problems which can be designed on similar basis. Realistic basis. Now, let us come to the more complex problems. For example, the whole question of plasmid instability. Let us come to the more interesting and difficult problems, plasmid instability. Now, suppose I was running a CSTR. So I was running a CSTR, and I have now cells in it which are all X positive, that is plasmid containing, and plasmid free cells are emerging X minus. And so the question is, after how long will they emerge? Now, I remember I wrote those following equations. Now, the problem is that mu is no longer equal to D. This is not true anymore. So you remember your bioprocess, right? I hope you remember mu is equal to D and all that stuff. Hello?
Yes, sir. Yes, sir.
You remember your basic material balances. You remember that dx by dt was equal to, the accumulation rate is equal to mu x minus dx. Dx is the outflow, mu x is the rate of production. So this is essentially accumulation is equal to reaction or growth minus outflow, because input of cells was 0. I mean, there should be a plus inflow, but inflow is 0 because the number of cells coming in. This is sterile feed. I'm sort of reminding you. But there is this is the material balance on biomass. Material balance on biomass. But what about the material balance on substrate? ds by dt is equal to dsf if feed is sf, and this is s, minus ds, where d into s, this is inflow minus outflow, minus mu x by yx by s, the rate of consumption of substrate, because if the rate of growth is mu into x, then divided by yx by s is nothing but the rate of consumption of substrate, because remember that delta x by delta s is equal to yx by s, the yield, and therefore dx by dt upon ds by dt is also equal to yx by s. And dx by dt, this term here is equal to mu into x, right? So you understand that the rate of substrate consumption will be mu into x divided by yx by s. If you're not following, please say so. If you're following, say yes. Otherwise, I can't see your faces.
Yes, sir. Yes.
Yeah, and of course, the third is the kinetic equation, which is mu is equal to mu max s upon km plus s. And solving these three equations together allows you to solve it. Mu is equal to d, and this equation, if you remember, these are all steady state, so these are all 0. Okay, and the second, this equation d sf minus s is equal to mu x by, I'm putting small x because of concentration factors, and these are all steady state values upon y x by s, which actually reduces to the fact that mu and d can be cancelled out, and so you can write y x by s, sf minus s bar is equal to x bar. Now this equation is very obvious because sf minus s, this is sf, this is s, this is the amount of substrate consumed, sf minus s. So if this is the amount of substrate consumed and the biomass is 0 here and the biomass is x here, this is the amount of biomass produced, x naught minus 0. So they too have to be related by the yx by s term because of this expression here. So delta x is nothing but x minus 0, and delta s is nothing but sf minus s, and therefore sf minus s is into yx by s is equal to delta x from this equation. So this is also material balance on substrate, and the third equation was mu is equal to mu max s upon km plus s. Now these are the three equations which allow you to create concentration values for what is the x bar, what is the s bar, what is the mu, etc., etc. And of course, you can write more equations for product, etc. for depending on how you write it. We'll come to the product part later on when we talk about translation rates and all that. We come back to genetics and we'll jump back to engineering later on. So this is all familiar stuff with you. This is just a revision. So I can quickly remove this. All of you are familiar with this?
Yes, sir.
Yeah. So
Yes,
now what happens with plasmid containing cells? You have to write dx plus by dt is equal to mu plus x plus minus dx plus minus p. Of course, this p is different, which I pointed out, but let us keep it like that, mu plus x plus. Where p is the frequency, if it is growing at mu plus x plus, a certain fraction p is getting converted to mu minus, so it is no longer part of this x plus balance. And dx minus by dt is equal to mu minus x minus dx minus, so this is plus, sorry, minus dx minus plus p mu plus x plus, because this is the amount of this here, this term here is being converted to this much. This is the rate of conversion of plasmid containing cells into plasmid free cells. So notice this is p mu plus x plus, this is p mu plus x plus, but here it is x minus, here it is x minus, here it is x plus, here it is x plus. Here it is all x plus. This is the amount of positive cells becoming negative cells. So in terms of number, in terms of the numerical quantity, this p mu plus x plus will be added to the numerical quantity here because this is the rate at which this is growing. Notice that these terms are no longer 0. They are not equal to 0. Because, and this is a very important point that I'm trying to make, that because this number is actually declining and this number is increasing. But it will turn out, as I can show you, that x plus x minus is a constant. Which means dx plus by dt plus dx minus by dt might be equal to 0. This will be negative, this will be positive. Because the total concentration of cells is not going to change. Why is it not going to change? Because I can write a substrate balance ds by dt is equal to input dsf minus s minus output, some steady state concentration minus, minus amount consumed by the mu minus x minus by y x by s minus mu plus x plus by yx by s. Now, if both these yx's by s's are equal, you can well imagine that I can actually prove that this is a true statement. Do you follow this intuitively, or do I do the maths? So the total cell density inside, total cell density will not change, but there will be positive cells and negative cells, and slowly the positive cells are getting converted to negative cells. But the total population is not changing. So the proportion, that is to say x plus upon x plus x minus, this is what is falling. The percentage recombinants is falling and the percentage non-recombinants is increasing. Now, I mean, some of you might create trouble, so I'm sort of say it easy enough, which is that we are assuming that y x plus s. Now somebody will say ये इसको x plus लिखिए, इसको x minus लिखिए. But बात सही है. You know, it's true. In the largest or the more complex models that you can construct, the yield of cells per unit substrate consumed will obviously be, sorry, the other way around. I'm so sorry. This is minus and this is plus. Okay, so now obviously the yield yx by s for a negative cell will be higher because this is delta x minus upon delta x s, and yx by s plus. Now we are getting into more complicated stuff which I don't want to talk about, but I'm sort of mentioning it. You don't have to sort of remember everything, but you know, just for some fun. If somebody wants to write a term paper on this, for example, that would be nice. Now these yields will be different because this fellow here is producing protein. So obviously less biomass will be produced for the same amount of substrate consumed. And this fellow is not producing protein, so it will be producing more cells per unit substrate consumed. Or you can get into all kinds of interesting, you know, structured modeling, which I'm sure we have not taught you, where you try to understand what is happening inside the cell in order to determine yield. And those are complicated questions because they require a modeling of all the reactions that are taking place in the cell and making biomass. So that is difficult biology and difficult maths. Let us not get into that, not at this stage. But you can well imagine that yx minus and yx by s plus may be unequal. If this is a small, if this is yield is higher, then of course the cell density will rise because now the cells will be utilizing substrate more efficiently. And so you will, but suppose they're equal, then this basic equation is fine. So now, given this equation, we'll have to write this expression here, and then we will have to write the two kinetic expressions, which is mu plus is equal to mu m plus s upon km plus s, and mu minus is equal to mu m minus s upon km plus s. So now you realize the problem. That is why I don't want to give these problems in class. So now the problem is that you have to solve all these differential equations, and you have to say that mu minus m minus, this term here, is actually greater than mu m plus. So really the basic point is mu m, it is the mu max because this is determined by substrate concentration. This is determined by substrate concentration. But, and this is important, you have the following. You have the following situation. You have the mu plus growing like this with respect to substrate concentration, and mu minus growing like this with respect to substrate concentration. So this is S versus mu. And notice that if the dilution rate is somewhere here, let us say this is the D. Remember, we used to solve it, you can solve it graphically. If this is D, remember, if mu is equal to D, then normally you would match it like this. Sorry, I should have drawn this. I didn't do it poorly. Right. Now, what it does is, if D is equal to this, notice that this is the substrate concentration that will be there in the reactor. Because this cell will become 100%. Now, at this substrate concentration, this cell is growing at a much lower value of mu than D. This mu minus is actually equal to D, but mu plus is actually much less than D. Can you see this? This is mu, this is X minus and this is X plus. And so this term here will be negative and this term here will possibly be equal to 0. If the dilution rate is somewhere here, then at this substrate concentration, this fellow will be growing faster, this fellow will be growing slower, and therefore this dx plus will be negative and this will be positive. And therefore this will increase and this will decrease. Are all of you following this argument?
Yes, sir. But like if D is equal to mu minus and mu plus is less than D, isn't it like a cell will after some time completely vanish? The concentration of the cell and the
then that is called washout. That is called washout. You should use the technical term. There will be washout, but the washout will be selective. Only the washout will take place only with the plasmid containing cells. Washout of X plus. But the plasmid free cells will actually remain where they are, and as the washout of plasmid containing cells takes place, the plasmid free cells will start dominating the population more and more. Because now you have a competition between two types, right? X plus and X minus. And this fellow is getting washed out. So suppose there are, I mean, just for your, suppose you have tensor of 8 cells per ml. And this is originally tensor of 1 cell per ml. Sorry, 1 minute. Can you hear me? Yeah.
Yes, sir.
Hello. Yeah. And suppose this is tensor of 2. So slowly, actually, this tensor of 2 will actually not be negative. It will not be 0. It will slowly start becoming positive because the substrate concentration will rise. Why will the substrate concentration rise? Because X plus is getting washed out. So substrate is not being consumed. So substrate concentrations will rise higher than mu minus for that particular dilution rate, and this cell will slowly start growing. So really, the way it happens is not like this. I should have drawn it much better. The way it happens is like this. I'm just going to draw it again. And this is important to understand because you would not have done co-culture. Have you studied co-culture in CSTRs? In your bioprocess? No.
No, sir.
Yeah, that is true enough. I mean, that's a trickier business to learn. And these are the two growth rates, right? Let us say these are two growth rates. Now, what happens is that originally this is mu versus D, and suppose the dilution rate is this. D is the dilution rate here. Now, the original substrate concentration is this because this is X plus and there is no X minus. There is no X minus. There is no X minus cells because they are not emerged in the population. So the cell is running with only X plus. Now, slowly a small amount of X minus cells emerge. And they, at this substrate concentration, actually have a growth rate equal to this. So they grow at this rate. which means that dx minus by minus is actually hugely positive and dx plus is equal to 0 still. But because they grow at this rate, this is x minus cells growing at this rate, because their mu value is equal to, at this substrate concentration is this. Because they grow at this rate, therefore they consume the substrate. So after some time, the substrate concentration falls. And it falls to this value, let us say. You still have, now at this value, there is something funny happening. At this point, the x plus cells start growing slower than dilution rate, and the x minus cells start growing faster than dilution rate. Right? And so you can see that what really starts happening is that these cells, this cell here is actually growing, mu minus is greater than d, while mu plus is less than d. Can you follow this? Because this is the dilution.
Yes, sir.
So the substrate concentration falls to this value. And so therefore x plus is disappearing and mu minus, x minus is appearing. It is building up. So there is a fast build-up of x plus cells. Finally, you actually end up with a substrate concentration of this value. This is the S final, where you actually see that at this value of substrate concentration, the D is equal to mu minus, D is equal to mu minus equal to D, and mu plus is now much less than D. It is here. And D is here, and you can see that all mu plus cells get washed out. So this is a movement from substrate concentration of this value to this value. So there is a decline in substrate concentration, and because there is a decline in substrate concentration, actually that assumption of x plus x minus is constant is slightly false. Because obviously, if there is a decline in substrate concentration, the total concentration of cells actually tends to increase slightly, and the substrate concentration falls. Because X minus cells are able to utilize and scavenge the substrate much more efficiently than X plus cells. But what it does effectively do is cause washout of X. Now, unfortunately, this is the only thing I can do. I do not know how to make a question out of it, rather than make you write these differential equations. Can you people handle MATLAB or Simulink? And can you handle OD? I mean, forget MATLAB. If I say MATLAB, you get angry, or Simulink is a part of MATLAB. I don't know. We used to use Simulink a lot. But really, what I need to know is that do you have, whether it is Python or whatever language you study nowadays? I mean, हमारे ज़माने में भाई साहब, we had to code in Pascal and Fortran in cards, and go to the main machine and ensure that we had not made any errors. So your life is much easier. So when we were students your age, we had to sit with packets of cards and punch small rectangular holes in them and then feed it to the card reader. So we had a very tough time. So I get very, naturally, I hope you don't get upset by my laughing, but I get very angry when students say they can't handle computers nowadays. I can't handle computers, I can only handle card readers, but you people should. So do you people have methods to solve ODEs, at least ordinary differential equations, or rather actually ODEs plus algebraic equations? So notice that there is equation 1, 2, 3, 4, and 5. So this is a combination of algebraic and differential equations, and this can be simulated with respect to time, and you get what I was talking about in the last class. I was talking about the fact that actually what you will tend to get is finally a very simple plot of x plus upon x plus plus x minus, which is the percentage recombinants. With respect to time, it goes like this. And as I said, if p values are small, then if the smaller it is, the later it appears. So these are p values of, let us say, 10 to the -5, this is 10 to the -6. This. So can you run such simulations in your ODE solvers? Is the question that I want to ask you.
Yes, sir. Like I don't know about MATLAB, but there are online tools which we can use, like all.
There are many
Mathematica
online tools which can solve a combination of ODE plus algebraic equations. I mean, there are too many. There are quite a lot. So you write these algebraic equations, put some numbers, and please produce some data. Can this be a good assignment, or I do not know what? And of course, so if you choose different values of P, you get graphs like this. And this percentage recombinants, actually nothing but percentage recombinants. And if I write percentage recombinants plot versus time for same value of P but different values of alpha, alpha being equal to now no longer mu minus but mu m minus upon mu m plus. Remember that we are assuming that Ks plus and Ks minus are the same. Their affinity for the substrate is the same. I mean, just like as I said, Yx by S is the same. A plus is equal to Yx minus. If you change these, then it becomes more, well, it is correct to change it, but it is not going to, it is going to be more accurate, but I'm not sort of doing it right now. And then if you can get plots like this. As alpha values change. This is alpha. Assuming that this is equal. So if alpha value is equal to 1.3 here, it is 1.2 here, it is 1.1 here. So if alpha values are lower, the decline will be slow. P values are lower, the emergence will be later. So do you realize the subtle difference between these two graphs? And so they will all emerge at the same time because I'm taking P is the same. So they will emerge at the same time, but they will fall gently as alpha is lower. Here, alpha is the same, alpha is 1.3, but P is different. So you understand? And can you please solve these questions? I don't know what kind of question I will ask because I cannot expect you to solve these questions, but yeah, that's the kind of questions you can think about.
Yes, sir, we will try.
Yeah, okay. So shall we now go ahead with the class? Because we have less time left and 10 minutes at least for the next class. Okay. So now we are now looking at, remember, codon bias, and really we were looking at, so DNA to RNA, there are all kinds. I mean, if you start getting into the maths of this, I'm sure you will get completely flabbergasted by the amount of work. Just now, I've sent your senior a BTech project where single cell and stochastic modeling and stuff like that have you people done any stochastic modeling ever? Population-based variations? Then I can talk something about stochastic modeling. Huh?
Not really.
No. Let us not get into tough business. Let us get the concepts clear and simple, because biology has enough complexity in itself to add mathematical complexity. But stochastic modeling is the way to go, because cells are noisy, and what you see is population combinations of population averages, but really the variations within the cell population is best understood in terms of stochastic modeling. But these are interesting things. Some of you might at some point get interested, because biotech, just like your other jobs which are much more well-paying, has a tremendous amount of intellectual and academic growth in the past 2 decades. And the major discoveries that are taking place in this is so remarkable that it's absolutely impossible to encapsulate it. As I said about this course as well, everywhere I put my hand in, I do not know how much depth I should go into, because I become very completely helpless, in the sense that how much of detail should be introduced to a BTech student set, because if we make it too detailed, then we'll lose out on other subjects. So now, really the mRNA protein, the translation step, is really the problematic step, because translation is not just a matter of rRNA and the tRNA, etc., but the tRNA has to be charged, and the charging process requires ATP, and NADH and NAD and all kind of, so this whole mRNA train sitting on the rRNA molecule, which you might have seen in some cartoons, etc., etc., and the mRNA train arriving here, and this is dragging in some tRNAs. Oh, there's a very poor drawing of tRNA, but anyway, sorry for that. Dragging in tRNA, and then this mRNA train giving rise to the nascent polypeptide. Nascent polypeptide being formed. These are, remember, these are happening in fractions of seconds. So this is a system which is damn efficient, but it does require ATP, NADH, energy molecules, rRNA molecules, all kinds of things. And all these things, and really my knowledge of biology is very poor, so I do not know what all things it requires, other than the very fact that, remember, and that's the most obvious point that I'm trying to make, is that the translation process is happening to the cellular proteins as well. The cellular proteins are also competing, and remember, cellular proteins comprise 50% of cellular mass. Now, so this is the elephant in the room. It is 50% of cellular mass is cellular proteins, and your protein product is competing with this cellular proteins as well. And so not only are you diverting the flux of, so the diversion of flux, and when I say diversion of metabolic flux, I really mean this as a vague term to capture the requirement of amino acids. Individual amino acids have to be brought along with the tRNA, right? The charged tRNA is charged with the amino acid. Now to charge it with the amino acid is required. To charge it, ATP is required. So how many molecules of ATP are required to join these amino acids in a chain? AA1, AA2, AA3. आपने कभी calculate किया है? Do the stoichiometry or the energy requirements to make a protein out of a set of amino acids, because the tRNA has to bring it and so on and so forth. So the metabolic flux is a combination of amino acids, ATP, rRNA molecules, and a large number of things. I'll call you back. Class going on. So, sorry. So this whole problem is not simple, because your competition for metabolites, critical metabolites, energy metabolites, etc., etc., is pretty high. And this competition creates this diversion of metabolic flux, or the diversion of critical metabolites, creates what used to be called by Bailey a metabolic burden. And it is this primarily metabolic burden which is responsible for the fact that mu minus is greater than mu plus. Because cells no longer can grow as fast as the cells which do not have to produce the desired recombinant protein product. So the protein product, especially if it is in large quantities, is a huge drain on resources and a direct competition with 50% of the cellular mass, which is really the cellular proteins. So this competition was termed as metabolic burden, because people could observe this. They could not see what was happening, but they could see that mu minus was greater than mu plus. And so they termed it metabolic burden because they saw this diversion of metabolic fluxes. Now, and this is very important, now we understand things much better than in the 1980s and the 1990s, where the term metabolic burden was used just like a vague statement to mean diversion. But the systems are not that simple. And really, what we see now is something much more complex. It is no longer the case that our understanding is limited to the fact that here is some metabolic flux, I will call it substrate. Here is some substrate going into some kind of metabolite, and these metabolites were originally going towards cell growth. And I'm sort of making a very broad, gross model. And now we are diverting this for recombinant protein, and therefore my growth rate goes down. So earlier it was called diversion of metabolic fluxes. This is not one single metabolite, it is a combination of 50 or 100 metabolites, amino acids, tRNAs, ATPs, etc., rRNA, the ribosomal machinery which does the translation. All this is included in this very broad term S going to N. Is this clear?
Yes, sir.
Yeah.
Yes, sir.
So now this is now understood in a much better way. Now cells have all kinds of sensing mechanisms which we do not even know about. Sensing mechanisms. So really the problem is that it is not that the cell cannot afford to lose some of the metabolites to recombinant protein. But the problem is that it says, hold on, what is happening to my growth? Why? Where is it going? Where are my metabolites going? Because recombinant protein is something completely new to the cell. It has never encountered it before. You have introduced a plasmid, you have introduced inside the cell some plasmids which are carrying genes. It is something foreign to its original evolutionary growth. It is something new, novel. And it says, what the hell is happening to me? Where are my metabolites going? It can sense the fact that there is a depletion or a shortfall of metabolites. And when it sees this depletion and shortfall, it reacts. How does it react? It reacts by saying, because there is a depletion, maybe I am not getting enough substrate from outside. Notice that it is yet actually getting substrate, but internal sensing mechanisms say that there is no substrate supply because there are no metabolites available for cell growth. So even though there is a lot of substrate available outside, the sensing mechanisms tell it that, well, there is no substrate available. And so the cell mounts what is called a cellular stress response. Now the cellular stress response is mounted under all kinds of response, and the most logical cellular response is mounted during starvation. So the starvation response or the starvation stress is also triggered when there is recombinant protein expression. The oxidative stress response is also triggered. And a range of stress responses which have been studied, heat shock, generalized stress response, stringent stress response, all these are various things that biologists talk about, and I will not talk about them in detail. I will simply call it CSR, which is a combination of multiple stress responses, because the cell is saying, hold on, where is my food going? It is like our country, na? Where was all the production going when we were, ruled by the British? It was all going to England. So our people were not getting enough. There was no growth. So what did we do? We said, hold on, we will stop production. We reacted and said, why the hell should we make stuff for others? And we stopped growing. We said we will have a strike, we will not produce for the British. Similarly, the cell goes on a strike and says, what the hell, I'm not interested in producing recombinant protein. Where is my food going for cell growth? I will stop eating. I will start starving. Well, it is not thinking, but my point is why does it stop eating even when there is food? Because it thinks that there is no food. Because it is not getting enough for cell growth, because all the metabolites are diverted away. It says, oh, hold on, there is no food. So what do you mean by stopping eating? It stops or down regulates genes which are involved in substrate uptake, because it senses that there is no substrate. And this down regulation of about 1,000 genes takes place, which is the cellular stress response. So about 1,000 genes get down regulated. Interestingly, a few hundred genes get upregulated, which are supposed to save the cell and do other things. So there is a complete, what I should say, this process leads to a complete reprogramming of the cellular machinery. This reprogramming of cellular machinery, and what is this reprogramming supposed to do? Yeah, any guesses? Why does the cellular machinery reprogram itself? Can you tell me? Because it sees that there is starvation, there is no food. So it reprograms the cellular machinery to ensure survival under stress. So the cellular stress response is nothing but a survival strategy. So it actually down regulates everything. It shuts down the cell so that the cell can survive for a longer period. Cells growing fast can make more cells, but they are very dependent on substrate, etc. And so when they see that there is no substrate, the survival strategy leads to a reprogramming of cellular machinery, leading to a shutdown. And that is why there is no growth, there is no substrate uptake, and mu plus cells. So this whole notion that mu plus is less than mu minus is a very simplistic notion earlier of diversion of metabolic fluxes. Now we understand that it is no longer diversion of metabolic flux. It is a much more complex reprogramming of the cell. So a lot of people have now tried to increase recombinant production by forcing the cell to eat, by introducing genes which take up substrate, by introducing genes on separate plasmids to increase ATP production or energy production. This is a very, very difficult job to sort of reintroduce the 1,000 genes that are shutting it down. So we try to make the cell not shut down. But cellular stress response, the CSR, is really the main mechanism by which cells shut down. And that is the reason why within 3, 4, 5 generations of induction, 3, 4 doublings. So within a very short period of induction of protein synthesis, you have heard of induction right now in the lab practicals, etc. The production of proteins is stopped. So notice that in metabolites, for example, you would have studied proteins can, metabolites are produced for hours and hours and hours, 100 hours, metabolites can be produced. But protein production never takes place for more than 3-4 hours because of the mounting of the cellular stress response. So until we understand cellular stress response, we will have production only for 4 hours. And therefore, things like, continuous bioprocessing, which is used for continuous production because people want CSTRs in their industry. Now, you can never do it for E. coli or any other thing for producing recombinant proteins because you have to take care of this first. And that is still beyond our scope because we are still not able to know how to handle this 1,000 genes and how to solve this problem. So this is...
For all the cells, reprogramming of cellular machinery happens, or like is it like 99% or 99.9%?
भाई ये तो किसी ने देखा नहीं है क्योंकि हम लोग की सैम्पलिंग single cell transcriptomics. Have you heard of the word transcriptomic?
Yes, sir.
आपने transcriptomic proteomics सुना है ना? तो ट्रांसक्रिप्टोमिक प्रोटियोमिक्स वर्क जो है वो अभी 10 साल पहले सिंगल सेल पे करना शुरू किया लोगों ने. सो रत्नेश, दिस इज अ वेरी गुड आइडिया. अभी तक तो ये रिसर्च हुआ नहीं है कि रिकॉम्बिनेंट प्रोटीन प्रोडक्शन में सेल का सिंगल सेल ट्रांसक्रिप्टोमिक्स करके देखा जाए पॉपुलेशन डिस्ट्रीब्यूशन क्या है. बट टिल नाउ द assumption is that moment there is a over production of protein, there is a cellular response and a shutting down, because we obviously do it with populations, and in populations we can see it. Whether there is noise, then again the other question will emerge. The cell which is not mounting a cellular response may well have also stopped the protein production from taking place. वो सब देखना पड़ेगा. Is there a cell where protein production is going on but there is no cellular response? ऐसा कोई रिपोर्ट अभी तक नहीं है. There is no such report. So we understand that cellular response is a dynamic response which actually feedback inhibits protein production by simply shutting down everything inside the cell. It is not that it shuts down protein production, it shuts down everything. Okay, and that is why translation is the rate limiting step within a few hours of protein expression, induction of protein expression. So we'll stop here. And next class we will talk about, within the next couple of classes I want to finish this recombinant protein production business and move on to enzyme kinetics, because that's also a large subject. Yeah, any questions? So that is what I wanted to tell you, that in the 80s there was this very simplistic notion which was a stoichiometric notion. Ki a little bit of food is going here, and a little bit of food is going here. So as this food amount increases, this becomes less. So it was like there was a supply side which was fixed 100, and this was all 100. When it becomes this, when this becomes 20, this has to become 80. When this becomes 30, this has to become 70. This was a mathematical notion of a constancy of cells. Now we understand cells as a much more dynamic system, where the fact that this is 20 will tend, the fact that this is 20 here will impact on how much supply will take place. So cell is a dynamic responder, and so metabolic burden is a dynamic concept. It is no longer simply the fact that there is diversion. It is the fact that recombinant protein triggers a reprogramming of cellular machinery, which then feedback inhibits both cell growth and recombinant protein production. So that's a more complex concept than, and with deeper understanding of transcriptomes and proteomes, etc., which allows us to understand that this is not a simple diversion, but a dynamic response. Anything else? Any questions? Now, these are things which are not there in textbooks. Unfortunately, these are all within the past 4 or 5 years of research and findings and concepts. So one is looking very hard to try to get you some books to sort of revise this. I will try to find by next, not tomorrow, but by this week, definitely. Any questions?
None currently, sir.
Okay, so thank you very much. I will sort of stop now.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you.